Hello everyone, it's February the 7th. Alright, first thing, so in React Native, there are something called scroll view, flat list, and all those things that you can scroll. And as you scroll, there will be an indicator coming out to tell you how far you have scrolled. And that indicator is something that's not very customizable. I mean, you cannot just do whatever you want on the indicator. And you can't even change the style very easily. You can, like in iOS, you can change the style, but I never use it. In Android, you cannot change the style. In Android, you can leave this indicator on all the time, but in iOS, you cannot even leave it on all the time. So that's a big shortcoming to a certain extent. Like, what if you want to customize your scroll bar, your scroll indicator? What if you want it to be a different color? You don't want it to be gray. You don't want it to be white. You want it to be, let's say, pink. How can you do that? And it just so happens that our app, really can use a customizable scroll indicator, because we need to show to the people who are using the app that it's the content is scrollable. But just using the default, it's just very hard, and we have some hack around it, but it never worked very well. So today I finally dig into this thing, and very grateful for a answer on Stack Overflow that kind of show the basic idea of how to do this, how to basically bootstrap your own scroll indicator. And I like that solution very much, because usually when you think about this, you're like, okay, we probably need to use a panhandler, and I did panhandler stuff in the past, and dude, that thing is wild. That thing is tough. And this solution doesn't use that. This thing just use on scroll, because the scroll view does give you this method on scroll, so you can get what they call is the content offset. You can get basically the position of the content at each moment while you're scrolling. And by that content offset, along with some calculation, some math, not very difficult, but it does take me a while to figure it out. And we're able to control a piece of animated view to go up and down as you're swiping. Now that comes from the solution, but I was able to figure out how to shrink that bar, because if you're scrolling, I'm not sure if it's here. It's probably not here, but as you're scrolling, yeah, something like here, you scroll down to the bottom. There's no more give, right? There's no more give. But on an app, when you scroll down to the bottom, the app allows you to go a little bit more to make it very, very, very bouncy. And as you do the bouncy, the scroll indicator will shrink. It gets smaller, it gets larger. Now that is something I figured out myself. I was very proud of myself. So basically, I did a copy, but a customizable copy of the original scroll indicator. Now, of course, it doesn't have all the features. At least I can think of one feature that is in the original scroll indicator. You can actually press on the indicator itself and then scroll up and down, which make it scrolling faster. In my version, you can't. I mean, maybe I can figure out how to do it, but nah, I don't want to figure out how to do it. So the current version is good enough. Yeah, it's good enough. I will write it into a package and publish on npm, but I have to wait until next week because I already done 2 days on the app. I have other stuff to do, but yeah, basically it was very good. Finally got it done. I got it so much that I didn't even train today. Well, it's okay. I mean, my wrist is kind of messed up, so take an extra day for rest is good. I mean, tomorrow probably I won't snatch or clean and jerk. Not sure, because tomorrow I'm gonna have to squat. So it definitely will squat first. Maybe I'll do snatch. I don't know. Maybe we'll do sweat. Well, yeah, maybe we'll do snatch. We'll see. All right, so that's one, right? And then look at what I did this morning. The difference between this accepted, we've basically done it, and the not accepted is just this thing, minimum. In the previous version, if you can see, right here, it's maximum, all right? So it shall be minimum. Now, the reason it shall be minimum, this is exact, it's a CPU problem. So what we're saying is, if we don't have anybody waiting, so everyone is on the CPU queue, okay? Then we need to pick out because the top will be the earliest task will be coming out of the CPU, but the current tick is smaller, so we have to wait to one of them to finish. And because both of them are bigger than the tick, right? You should take the smaller one because that one will come out first. But unfortunately, I in the yesterday's version I picked out the bigger one, and of course it's not going to be correct. So it's supposed to be the minimum, and when you do minimum, it passes, right? It just passes. So yeah. I probably will read into. I think I'll go look into the discussion a little bit. Maybe I'll even publish the solution, just in case. I need to also write here, but you know what? I'm gonna wait because we need to do today's things first. That's the priority. All right, so it's a jump game. I think it's one of the old jump game. Just get this done, and then we will update this, and we'll call it a day. Okay, yeah, it's a good solution. All right, let's do this. Jump game number 2. A zero-indexed array of integers nums of length n. You initially position as 0. Each element nums I represents the maximum length of forward jump from index I. In other words, if you are at nums I, you can jump to any I plus j, where this small equal to j small equal to nums I and I plus j small n. Return the minimum number of jumps to reach nums n minus 1. Test case guarantees you can reach. Isn't this just the what are you thinking? Isn't this just the, my God, think, what you going to say? DP. Yeah, I think it's just DP, right? So we go from right to left. We start from this, right? It takes 0 step to reach here. And then for here, I'll take, this one will take, how many steps will take for this one to reach the end? Well, it's the maximum, right? The maximum length of forward jump. So if I know the from this one to the end, what's the minimum number of jumps to get it? Now I have this. So what we need is to know from me, I have all these I can reach. So what's the minimum among these things, right? What's the minimum among these things? So we need to check one by one to find the minimum, and then that will be the minimum for me, right? But it can be done if we know, given a range, what's the minimum. So if I know the minimum from this towards the end, isn't this just the solution? From this towards the end, right? If we start from here, what is the minimum? And then we start from here, what's the minimum? Can we do a prefix minimum type of thing? A prefix minimum. So we say the minimum start from here. The minimum starts from here. Nah, it needs to be a range. It needs to be a range. Otherwise, we have to go through every single one. But it's 1,000, so maybe it's okay if we do it the other way. Let me check the first one. So the first one is 0, right? And then for this one, we'll take 1. We show the minimum to see if it can reach the minimum. Will take 1 step, right? And for here we can reach, so it takes 1 step here. Right, and then we say we can do 1, so we have to check this as 1. So for this one, it's take 2 steps. For this, right, basically we need a smaller of this 3. So this one's actually 1 step because we have to take 1 step. And for this, 1, 2, so I need to pick smaller of the 2, so we take 2 steps. So I need a smaller of a range. And I do not want to use plus. That's not bit because I need the actual value. So we need to give me a range to give me the smallest value within this range, right? And then what you're gonna give me is the smallest value. No, I don't want the smallest value within this range. It should be the smallest value in this specific range. How can I calculate that faster? Yeah, that will be 1,000. Maybe I can pass, right? Maybe I can pass. But I feel like there gotta be a better way. And I do not want to do segment tree. My segment tree definitely works. You can do segment tree, but can we do another way? I don't know. Maybe we can try it, but I'm pretty sure it's gonna time out. Like seriously, dude. I think it's gonna time out. Yeah, we can try it. If it times out, which I think it's very likely. I just don't want to do segment tree. That's all it is. There's no any reason. I just don't want to do segment tree. I simply do not want to do segment tree. Minimum. Plus 1 to what? To I plus nums I. Right, that's the maximum you can reach. And of course, shall be the minimum of this and n. dpi equals the minimum dpi and 1 plus dpj. I'll return dp0. Yeah. I think. Nah. Oh. The hell? That is strange. How come? What? Three. 0, 1, 2, 3. Yeah. It'll be 4 to 3 plus 1 is 4. Ooh, that should be plus 1. I don't know. Yeah, I think we're in timeout. Oh, we got lucky. We got lucky. We got lucky. We didn't time out. Do we have the same problem? Same method as the previous time? 92. 109. What was this method? Nope. That's better than this. Okay, this is there is a better way. I don't like this. This is OMN, right? Where n equals line nums, and m equals maximum nums I, max nums. It's dp, but very poorly. Alright, now we need to figure out how can we make this one better. You see the difference in time, 30 something. Let me think. Let me think. But this is also the DP method. Yeah, this is also the DP method. But back then we only have 92 test cases, so it's okay. But now is different. Now is different. We need to figure out a better way. I did saw you say BFS. I don't know how BFS is gonna have to do with this. BFS. Huh. BFS. So 2, which means from this node, right? So node from node 0, I can go node 1, node 2, node 3. No, only node 1, node 2, plus 1, plus 2, 0, 1, 2. And from node 1, I can go to 1, 2, 2, 3, 4. Right? 1 can go to node 2. One can go to 2, 1 can go to 3. And 0, 1, 2, 3, 4 can go to 4. And from 0, 1, 2, from 2, I can only go to node 3. And from 3, I can go to node 4. So now the question is, what is the fastest way? Oh, damn. So 0 to 1, and then to 4. So, oh yeah, that is a DFS. To see when do we first get to it. Holy crap. And if it's already in it, we don't put it in again because we can reach it faster. Oh, that is, I saw that. Take a glimpse. We have Q. It's actually be a set. Why don't you do visited? Okay. And then we say while Q, right? Temp equals this for n in Q. Visited.add n. Right? And then for next in, oopsie doozy, I need its, oh yeah, n is already, oh, let's call it I, index. All right, next in, range, I plus 1 to minimum I plus nums I plus 1, n. If next is not in visited, temp.append next, blah, blah, blah. Set steps as 0. Right, I'm going to say if I is equal to n minus 1, now we can return steps. Then Q equal to time, steps equals 1. What do we return? We shall return so that's step 0, and then this is step 1. Yeah, I think we should return steps. It should be good enough. Yep. Huh. Something is not right. That's interesting. Maybe we need to do this for I. I think this has to be set. That will make sure the next round we won't have any repeat. Now the next round will not have a repeat because I start from here. I add all of those, right? But we just need to make sure the ones I add is not already visited. It has nothing to do with this. It has nothing to do because the next one is not being visited. Right, if I do this, right, and I do this, and do this, it's not invisible. No, you know what? I think this is important because the next level I can have all of them. Right, the next level I can have all of them, and then it will be important that there will be overlap. Yeah, I see there will be overlap. So this is kind of is important. I have to use set. Ha! Just slightly faster. Alright, so what was the magnificent solution? What was this magnificent solution? BFS with single pass. It's greedy as well. Huh? Next and we try to go as far as we can. Next and is next and I plus the further we can go. If I can reach it, we're done. If not, I have current and. If I is larger or equal to current and equals next and. Oh, so this basically is greedy. Everyone will try to go as far as I can. Okay? But if I cannot, what is I? I is every single one. Wait, what? If I is larger than current and next and I is larger equal to the current and so we move the current end to this, which means one step the furthest we can go is here. So the next one coming up. So next one coming up is from this one. What's the furthest it can go? Right? And then there's the next one. If it's larger than this, but if it's not, then basically, I see what it's doing. Everyone we try to see what's the furthest you can go in the first step. Okay, the furthest you can go. But it makes sense, right? But it makes sense because if you think about the graph, if you don't do greedy, right? You're saying there's some other way. You just don't go the maximum you can go. But it does not go the maximum you can go. Because the first step, it goes to 2. I don't understand this one. So each step we try to go the maximum you can go, right? So like at the first level, okay? At the first level, we can hit many different positions. Okay, at the first level, we can go to many different positions. Right? Start, we can hit these positions. And then we move on to here. And from this position, we hit even further. If you're within the previous current end, that means you can be reached in one step. Yes, I think that's what it means. So you're at a certain point, we say, okay, from here I can go all the way down, and then I can reach any single ones inside, right? And I'll just try go one by one. And if any one of these can reach even further, right? So we need to, that would be a new end. Current end will be the new end. And we just say from this one we'll go here. So basically, we just trying to find the first instance that we can reach the end. Because we want the first one to go to the end. A very smart very small PFS. Yeah, it is the same. It is exactly the same. It's the same because when you hit the first one, all right, and you have certain things you can go, and I use the largest one because the first one, but you can look at this, right? The next is everybody. So what I want is to find whoever is the biggest so we can reach the maximum, right? We can reach the maximum, and everybody, which is this, right? This is the maximum you can reach. This is the maximum you can reach, right? Which means from the first one, you can always reach there. So anything in between, you can reach just by going the first one to +1, right? You can always reach anyone in between, so that's fine. And then you go one by one. It's just like you're going this. This is where you go one by one. You just add to the next level, right? But you just go one by one, and each one you can go to the furthest, right? So the first one you can go to the furthest will be the solution. Yes. So now the question is, because every time when you go to the largest, yeah, this is what you can do. And then if you extend the largest, that means you're on the next one, which means you'll take one step to move to the next one. So that's why you will have to increment the steps. You move on to the next one. And if anyone that's on the smaller, which is fine, I don't really worry about that. So when do we need to update? It's when do we need to update? I think it's when I'm here and I can reach beyond, right? I can reach beyond. That's we're extending the next end. Well, we just constantly extend like that. We reach the next round where I is larger than the current end. Yes, because that is the end of the current level. The current level is, this is the current level. So the end of the current level is this thing. This is the current level, right? This is the current level. So once we go beyond this current level, that's the next level. So, oof. All right, let's see if we can put this together ourselves. One pass BFS. Now the idea, well, is to find the max reach from each eye. All right, max reach from each eye, from the first, from num0, from 0, right? Max reach from num0. Then as we iterate from nums from 0, right, +1 to 0 plus nums0, we are always on the same level, right? We're always on the same level, and we update the max reach when I when we go beyond 0 plus num 0, we are at the second level, right? We're at the second level. We're at the second level. Keep doing this until the first time that max reach goes beyond nums. Yeah, this is O n. M. Same, because we have this, we have to go through all these times. But this will be O n, will be irrespective of the m. And we don't need Q. We don't need this, we just need steps, right? I'm going to say for I in range. Oh, there's a trick I remember I saw. Why we don't do n minus 1? Let's try what's going to happen. We do just go to n. Right? We're going to say max reach equals current level and both is 0, right? And then we say max reach are equal to maximum max reach I plus nums I. This is the max reach. And we say if max reach is larger or equal to n minus 1, then we shall return steps. That should be steps plus 1, right? Because if we have the max reach, it's from this we can go to the end. But this step, like if it's beginning, it would be 0. So yeah, so it has to be plus 1. Otherwise, if max reach doesn't do, then we just say if I is larger, shouldn't that be larger than, because the current end is 0. So when we hit it, right? When we hit it, yeah, when we hit current level end, because when we hit it, we prepare for the when we hit this, that means we need to prepare the next round. So we finish this step, right? So we say current level n shall equal to max reach and steps plus equal 1. Says finish traversing the current level, right? Update the level end for the next level. Does it work? Edge case 0. Shall be 0, right? Holy crap. Now I can do this. Right? We just return 0. Otherwise, we at least need to make 1. Because the last one is irrelevant. Try this. Yeah. Oof. It was a significant improvement. Sliding window. Okay, this is a max jump. It's all right. This is really good. Okay, so we're done with this. Come back here. This is what I'm gonna do. This is basically a CPU scheduler. We have 2 tasks. One on the left and the other on the right. When a task is done, the worker needs to wait for the for his turn to cross the bridge. Thus, we create 4 heaps. L wait, left wait queue. Workers here have completed their tasks, and wait for cross. CPU, left CPU queue. Workers here are actively doing the task. Right, wait, same as left, wait, but for the right, for the workers waiting on the right, right CPU, right CPU queue, same as right, should be R left, wait, art CPU, left CPU, but for the workers doing the task on the right. So the worker, a worker is represented by an array time tick, available time tick, efficiency, what's the last one, and it's index. Right, now available time tick is the value, is the time tick at which the worker finishes the task and is able to join the wait, join L wait or R wait. Know that when a worker is all the workers in the wait queue have available time tick equal to 0. Efficiency is the sum of left to right time and right to left time. In the implementation, efficiency must be the negative of the sum. Index is the index of the worker. In the implementation, index must be negative as well. Thus, in the heap, the worker with the smallest available time tick, that is the worker who will finish the earliest, gets to the top. If the available time tick are the same, e.g. in the wait queue, the worker with the larger negative efficiency, that is lower efficiency, gets to the top. If the efficiency are the same, the worker with the larger negative index, that is bigger index, gets to the top. The workflow goes like this. At the beginning, everybody is on the left wait. We pop the first worker and has him cross the bridge. We use a variable tick to keep track of the current time. Now the time spent crossing the bridge, right, is the time everyone has to wait. We update tick. We update tick for that. Once the worker is on the right side, we compute its available time tick as tick plus as the current tick, right, plus the time needed for him to complete the task on the right. Then we put him in the our CPU. Then we need to check if anyone, well, to check first we need to check if anyone on the CPU queue has completed their tasks, right? The check is to compare the current tick with available time tick on each worker, right? If the tick is larger than available time tick, the worker has completed the task and shall join the wait queue. Do this for both L CPU and R CPU. Right. Then we check whether we grab workers from the wait queue. If only L wait is available, as in the case at the beginning, we pop the worker from there and have him cross the bridge. We also use a variable tick to keep track of current time. Okay, time spent crossing bridge is the time everyone has to wait. We update for that. So on the right side, we compute its available time as current plus time needed. Put him in our CPU. If R wait is available, then regardless of whether L wait is available, we always pop workers from R wait and have him cross the bridge from right to left. We update tick for the current time, right? We update tick for current time and compute the available time tick for the worker working on the task on the left. Then we put him in left CPU. Now, last case. If neither L weight nor R weight is available, that means the current tick is smaller than available time tick from both L CPU and from the top worker on both and R CPU. Then we need to fast forward tick to the smaller of the two, and then repeat the process. One complication is that once all jobs have been picked up, we need to terminate the process above. At this point, there are still workers on right CPU. Yeah. But we don't care about left CPU or left weight anymore. We just want to get workers from right CPU to right weight to crossing the bridge. So the overall, I would say O(n) log k, right? Because at most I have k. Well, actually not. Time, yeah, time. The length of time is k. So O(n) log k, I would say. No, not this one. That's this one. I don't know. People don't like it, huh? I'm gonna post this. We can actually do this. I in range k. Heap q dot heap push L weight. And I think this one I can just go this. All right. Post this, not post this. Double check one more time. Yep, it's good. Simulate CPU schedule. We might be able to even simplify this. Cross. Wait. CPU. Tick. The time, just cross time. So current will pop on the wait. Right. Ooh, but how do you know? Oh. We do need time because the index is inside. Time, tick. Left to right. Is left to right. Wait is gonna be a so I shall equal to 0 if is left to right, else 3. So this will be I. This will be time. No, 0 or 2. This will be I plus 1. And then we push to the CPU. The return current. Do I need a current? Don't think I need current. So I don't even need to return current. I just need to return the int. So current is not necessary. I'll delete this. Right? And then this one has to do. This one has to do. So this one will be cross. Right, left wait, right CPU, time, tick. Is it true? true. And now we return a new tick. And now we tick equals cross. This time it'll be false. Okay. Ooh. Oh. Cross. Time tick false. Nope. Oh, yeah, we don't know. So we can do cheeky like equals this. If R wait, else R CPU 0 and 0. Something like that. We can remove this. Okay. One more time for good measure. That's good. Cross. Okay, that'll be it.